Theorems that we should look at. And let's look at the first one, in which we have for every A and B belonging to the set of real numbers, where let's take the case in which A cannot be 0 and B cannot be 0, and for every n belonging to the set of natural numbers, all right? And let's see what we may say. Let's break this up into various parts. A divided by B, all raised to the nth power, you would like to say is equal to, and Glenn?
A to the n.
A to the n.
All over B to the n.
All over B to the n. And I think, without going through the proof of this, I think that certainly you would accept this statement. Suppose we had A over B raised to the opposite of n power. And I think, in fact, there are two statements that we may write here. It may then be thought of in terms of A to the opposite of n divided by B to the opposite of n. And we may also say that this is equal to, and perhaps this is the more important part of it, Michael.
B to the n divided by A to the n.
B to the n divided by A to the n. Very good. And then, of course, if we happen to have A over B raised to the 0 power, well, let me first include the case in which we may think of in terms of A to the 0 divided by B to the 0. And again, perhaps the more important aspect of it is that this is equal to, and Tim says
1
is equal to 1. Very good. Well, let's look at one or two examples that perhaps will illustrate some of these theorems. And let me pick out some rather straightforward examples. Suppose we had something such as 12a squared b divided by 3ab squared times, and let's say 4a divided by 3b, all raised to the negative 1 power. And let's see now. If we didn't have this second factor here, we have certainly one that we're familiar with. 12 over 3 is another name for what? 4. A squared over A is A, divided by B over B squared is B. And now let's then use this theorem in which this is times, and what then would we like to say here for the second factor, Doug? 3B divided by 4A. And here now we may think in terms of one of our other theorems that we have been using, and without putting in all of the steps, 4a divided by 4a is a name for 1, and b over b is a name for 1, so this then is all equal to simply 3. Is that right? Okay. Let's look at a second example of perhaps that involves this theorem. Suppose we happen to have a binomial x plus 2y divided by, say, x minus y, all raised to the negative 1 power, times, and suppose we had some trinomial x squared plus 3xy plus 2y squared, all divided by, let's say x squared minus y squared. And let's see what we may say about this. And now again, notice that this is all raised to the negative 1 power, and so another name for this left factor here would be what, Steve?
X minus y.
We may think in terms of x minus y
Over x plus 2y.
all over x plus 2y times, and now looking at this second factor, perhaps we may factor that numerator, and does anyone see what that would factor into there? Rick?
X plus 2y.
X plus 2y times an x plus y. I think everyone will agree that we get a plus 3xy in there, and a 2y squared. And looking at the denominator, you recognize a pattern there, Kirby? We have here x squared minus
plus y
x plus y
times x minus y.
times an x minus y will then factor, x squared minus y squared then will factor into that. And now we look for names for the number 1. Again, this is a theorem that we had proven in our previous lesson. X plus y over x plus y is a name for 1. And what else do we see here? X minus y divided by x minus y is a name for 1. And by golly, x plus 2y divided by x plus 2y is a name for 1. And all of this then is going to be equal to 1. And please think of it as the number 1, not 0, certainly. Well, let's then look at that second theorem. Perhaps we want to move over here somewhere. Oh, I think we'll have some room in here in which perhaps this theorem I think is probably more important in terms of what we'd like to do. For every A and B and C and D belonging to the set of real numbers, let's exclude 0 for the case of B and C and D. All right, those numbers cannot be equal to 0. A divided by B, A over B divided by C over D, you would like to say is equal to, and this comes from some of our earlier work in arithmetic, Tim,
A over B times D over C.
times D over C. And in fact, relying on one of our theorems that we have already proven, this is AD over BC. Is that right? And let's run through the proof of this. I think it's quite straightforward, but certainly I think important enough for us to do it. Here is our statement and the reason for that statement. Let's start out with the left-hand side, and let me use this division symbol and go back to one of our meanings, or one of our original meanings of that symbol, and let me simply give, for the reason here, definition of division here, all right? Now, looking at this right-hand side, how may we write that? Let's look at it as A over B times, and what would it be? Times what? Well, not quite. 1 over C over D. And our reason for this is simply what? This is our relationship between what? Relationship between multiplication and division. Is that right? Now, let's look at 1 over C over D. And what's another name for 1 over C over D? And this has to do, we saw this once before, this has to do with what? Some property of, and a property of reciprocals. Is that right, Peter? So that 1 over C over D has another name, which is what? C over D. Is that right? I'm sorry, D over C. Is that right? And so then right here we may say that this is equal to A over B times, and it would be times what? And here it is D over C. Let me simply give there the property of reciprocals as our reason for this. Actually, we're practically done. If we then were to say this is AD divided by BC, and our reason for this is some product of quotient theorem that we have looked at before, product of quotients, which is a theorem that we have stated in the past. And let's include this as step 2, and step 3, and step 4, and I think then you will agree that we've proven this theorem. A over B divided by C over D then is equal to A over B times, in fact, the reciprocal of C over D. Is that right? Which is D over C. Well, I think this theorem is going to prove to be quite important for us, and let's look at a number of examples that will illustrate it, and let's see how we can go through them. Suppose we had x squared minus y squared divided by x squared y, and all this is then divided by x plus y over xy. All right? And now again, let's work vertically here. We would like to set it all up in terms of factors, certainly, and then using the theorem we can invert here and multiply, if I may use that phrase. X squared minus y squared, Peter, will factor into
X plus Y
x plus y
times X minus Y
times an x minus y over,
X squared Y.
not much we can do with that, x squared y times, and then let's go right into our theorem, times, Peter,
XY
xy
over X plus Y.
all over an x plus y, and you say, aha, the problem is rigged. X plus y over x plus y is a name for 1. Notice this bookkeeping method that I use here to describe this. Now let's see, y over y is a name for 1, is that right? Now perhaps here the bookkeeping method falls down a little bit because I don't want to cross out the x and the x squared, certainly. So perhaps right there I would rather simply do that in my head, so to speak. And what then is left but, Peter?
X minus Y over
X minus y over x. Does everyone agree with that? All right. Anyone want to go for x's here? X over x is a name for 1. And why not? From our last lesson, we said that what? It must involve multiplication. We need factors here, and certainly we do not have a factor. Well, let's look at another example. suppose we had something such as 3a minus 6 divided by a squared minus 9. All of this then is divided by 3a plus 6 all over, well, let's say we have a squared minus a minus 6. And let's see what we can say about this in our numerator. Well, who would like to start and see where we can go? Michael?
Well, you can take out a 3,
3.
so you have 3 times a minus 1.
3 times an a minus
2, I mean.
2, all right, divided by
An a minus 3
a minus 3
times an a plus 3.
times an a plus 3.
And then you divide, but you have to invert it.
All right, so this is times
A minus 2 and plus 3.
a, let's see now, what do you think? Because we
No,
have a
minus
minus
3 and
1a
plus
in
2.
here, it's an a what?
Minus 3
3
and plus 2.
times an a plus 2. Does everyone agree with that? And now let's see, in this numerator here, which is going to be in this denominator, it will factor into, Michael,
3 times a plus 2.
3 times an a plus 2. Does everyone agree that we factor this as much as possible? And now let's look for names for the number 1. Here we have a minus 3 over a minus 3, 3 divided by 3, and there's an a plus 2 divided by an a plus 2, and whatever is left then is our final result, our most simple name for this expression, which is, Malcolm,
A minus 2.
a minus 2,
over A plus 3.
all divided by an a plus 3. Notice, by the way, that a certainly cannot be equal to a negative 3, but not only can a not be negative 3, but from our original expression here, in order to say this then is equal to this, a cannot be equal to a positive 3, and a cannot also be a negative 2. And remember what our agreement was in our last lesson, and that is that every time the variable is such that the denominator is 0, then in fact we will exclude that number from our domain. Okay? Let's look at another example, and I think that's probably all that we need to do for today. Suppose we had 4a squared minus 4a divided by 6b cubed times, and now let's say that we have something such as a squared minus a minus 6. And let's put a little bit of a twist in here and think of this as 9 minus 3a, and now divided by, and suppose we have 2 minus a squared all over 18b cubed. All right? Now notice here we happen to have 3 factors, and let's just take it from left to right as we normally do, using our rules for multiplication and division, and when they occur then we will simply do them from left to right. Well, let's see now, what can we do here, and who would like to help us out? Tim?
4a
4a
times a minus 1.
times an a minus 1. Does everybody appreciate the fact that that's 1? Divided by
6b
6b cubed. Not much we can do about that. Times. And now here in this numerator,
a minus 3
a
plus
minus 3 times
a plus 2.
a plus 2. Now, notice here that we have 9 minus 3a, and here we have, for example, a minus 3. And perhaps it would be nice to treat that as what? What do you think we may do there? 9 minus 3a. Suppose we then were to factor, say, a negative 3. Let's think in terms of this number negative 3 times whatever is left, which is what?
A minus 3.
a minus 3. Does everybody agree with that? All right. Now this is then times, and now if we were to invert this and multiply, we have 18b cubed. Now, here we have 2 minus a squared. And perhaps we would like to think of this, let me just write it up here simply for a bookkeeping device. Let's think of that as negative 1 times, and what then would you like to do there but to write this, Tim?
A squared
a squared
plus a
plus a
minus 2.
minus 2. Now let's then think in terms of that as our factor here, which is negative 1 times, and possibly you can factor this into what? Bill?
A plus 2 and a minus 1.
a plus 2 times an a minus 1. Does everyone agree with that? Now, let's see what happens. Notice now everything is in the form of factors. Is that right? We have multiplication throughout the entire expression, both multiplication and division certainly. And let's look for names for the number 1. Now, negative 3 times a negative 1, of course, is 3, and 3 times 6 is 18, and lo and behold, there is a name for the number 1. All right, isn't that rigged? Now, let's see what else we have. A minus 3 divided by A minus 3 is 1. We have what? A plus 2 over A plus 2 is 1. And we still have A minus 1 divided by A minus 1 is equal to 1. And the whole expression then reduces to... Oh, we still have a B cubed divided by a B cubed, which is a name for 1. Good. And the entire expression then is equal to what? 4A. And you say, well, I think that the problem was set up so that there are lots of factors. Normally, this is the case, certainly for purposes of practice and reinforcement of these theorems. Certainly, the problems are set up so that there are some factors. Don't be surprised, however, if occasionally there are no factors. Well, let me give you your assignment. This will be assignment number 48.